Hello YouTube, this is my first video in which we're going to look at techniques for evaluating limits that don't necessarily involve making tables of values or looking at the graph, but really just working with them algebraically. And so we're going to take the approach of looking at tables and graphs in order to build up to this, but the first limit we're going to look at is actually this one we've got listed right here. The question becomes this: we say, what is the limit of this function, or what are its y values approaching arbitrarily close to as x is getting really close to -3? So I would like to evaluate this limit, and my primary methods are going to be using tables and graphs. So what we're going to do is this: we're actually going to pop over to GeoGebra here, and I'll head down here to the input field, and we'll take a look at what we want to put in here. But our function, we'll just call it, how about f of x? F of x equals, and it's a quotient of two polynomials. So we'll head over here, we'll type in x squared, I think it was plus x minus 6 is what I have, and then in the basement it seems that we have x plus 3. Okay, so I'm going to go ahead and hit enter, and we can see that we get this linear function right here, or seemingly linear function, even though it's a rational function. Okay, and what we're asking really is this: what is the limit of this as x approaches -3? Now, before we kind of come up with a estimation for this here, what I want to point out is this: in prior explorations, all we've done is really directly substituted in the value of say, we call it, this is like the c value, into the function to see what we would get here. And I just want to show that direct substitution actually fails in this instance. If we were to plug in everywhere we see an x, if we were to plug in -3, what we end up with is this expression right here, in which we get a -3 here, a -3 here, and a -3 down here. Instantly, we can see that this is going to result in a 0 in the basement, and if we actually evaluate the top, we get a 9, and this would be plus a -3 plus a -6, which actually also results in a 0. So the first thing I want to mention about this is we get this 0 over 0 form, and this has a name. It's actually referred to as indeterminate form. Okay, and so when we talk about indeterminate form, we're talking about a fraction of the form 0 over 0, but basically, I mean, this isn't, like an undefined sense. We basically just say there's really not much I can say about this, and there's a reason why we ended up with this indeterminate form, but it doesn't mean the limit doesn't exist. It simply means that we cannot evaluate it exactly at that x value. So what we're going to have to do is we're going to have to observe what it is approaching as x approaches -3. So now, I suppose one thing I kind of want to go through is this: well, what if, I'll throw a point on our function here, and we could slide this point left and right, but we say as our x values are approaching -3, that is, as our x values are approaching -3 from the left and the right, what is the value of our function actually approaching? And it looks as if, see, you notice that the point just disappeared right there, and actually I don't even know how to get it back. It's almost like a black hole exists right here. But if we could zoom in, you would see that this function exists everywhere except for at this point right here. It doesn't exist right here, but we can still see that the y values are getting really, really, really close to, it looks like, a height of -5 as our function approaches this. So based upon the graph, I would say simply, well, the limit of this function as x approaches -3, we're just going to go ahead and say it's -5. Also this, we can look at this from a perspective of a table. And so in order to do this, since the limit we're taking here is as x approaches -3, I'm actually going to open the spreadsheet over here, and we'll put in x values on the left. So I'm going to hit -3, and since we're going to -3, we'll go a few to the left of this. So this would be -3.01, this would be -3.02, this would be -3.03, oops, let's try this again, 3.03, this would be -3.02. And if we were to go a few values greater than -3 to the right of -3, this would be -2.99, -2.98, and -2.97. And so these being our input values, just a short list here, what I'll do is this: we'll type in f of what we have here in cell 1, which is -3.03, but we have to type in f of a1. Okay, so a1, essentially. And it says, well, if you were to plug this into your function, you'd have a y value of -5.03. So basically, just to the left of -3 here, at -3.03, we're at a height of -5.03. Now the nice thing about this is I can actually click and drag this down. It'll repeat the formula for all of these, and you'll notice, if you can see right here, it says exactly at -3. I seriously can't tell you where you're at. I mean, I really don't know, but you can see that as our x values are increasing and approaching -3 from the left, or approaching -3 from the right, our y values are getting arbitrarily close excuse me, to this height of -5. So this simply just further supports our claim that -5 is what the value of this function is approaching as x approaches -3. Okay, so when we end up in situations for which we have a direct substitution that produces this indeterminate form, the 0 over 0 form. It's not that all hope is lost algebraically speaking. Of course, if I had a graphing calculator, I would just graph it, look at the graph, looks like it's approaching -5, make a table of it, it looks like it's approaching -5 in value. But what do you do if you don't have those, resources available to you? And so we could actually evaluate this algebraically. Okay, so the way we're going to do this is we're going to use something that we call the dividing out technique. Okay, and so the dividing out technique, is dividing out. What I'm basically implying here when we say the quote-unquote dividing out technique is that maybe the top and bottom of this fraction have common factors that could have vacated the premises in the first place. So for instance, if we were to rewrite this expression, which we know was as x approaches -3, of this polynomial over the bottom polynomial, which was x plus 3, I noticed that the top factors down into x plus 3 and x minus 2, which instantly I recognize is being this. So we'd say, well, it could be rescribbled as the limit as x approaches -3 of the expression x minus 2. Okay, so few comments I want to make on this before we kind of proceed. First of all, we now have an expression in which we can directly substitute this value in. And had we directly substituted this in, we would say, well, then the value of this would just be f of c, where this is our c value here. We would have gotten this. We would have gotten -3 minus 2, which equals -5, which indeed was the limit that we had found up top in the first place. So we could have found this limit simply dividing out common factors between the numerator and the denominator in the first place, and then evaluated the limit for the leftover expression. But the second comment I want to kind of dig into is this. This function right here, this is not the original function we started with. Our original function was this one up here, and we referred to it in GeoGebra as f of x. And what I want you to know is f of x and g of x are two separate functions. They're entirely different. Okay, x minus 2 is not the same thing as this expression up here. However, what I want to do is I want to graph g of x, which is x minus 2, and say how do its values compare to the values of f of x that we started with. So heading over here, we'll go ahead and take f of x. We'll just unhighlight it here. It's not gone. It's still there. And we're going to type in g of x. And g of x, we said, was this simplified form of the original expression. So we'd say x minus 2. And of course, this is a linear function. It has a y-intercept at -2 right here, and goes up 1, right 1, up 1, right 1, up 1, right 1. What I want to notice is this. How do its y values compare to the y values of the original function to begin with? And what you should notice is this. If I even click this back on, boom, you notice that it's laying right on top of it. They have all of the same y values, every single one of them the same, except for one of them. For the case of f of x, we know that it doesn't exist at -3. It doesn't have a y value right there. It would have like an open dot, we call it discontinuity there. Whereas x minus 2 has all of the y values. It's clearly defined for all values of x. So what we can say is this, and this is kind of the profound thing. Actually, let me just go ahead and type this up over here on our table. I'll even type in g of cell A1 here and click and drag these values down. You're going to see that all of these, every single y value agrees except for this one right here. And it is the case that if it is the case that all y values agree for two separate graphs, except for at one point, then they must have the same limit at that point, regardless of whether or not one exists or not. So, I mean, we could have said that without graphing x minus 2. We could see clearly here, hey, look, it looks like it's getting really close to a height of -5 as we come in from the left and right of -3. So, essentially, the dividing out technique basically states that if this function right here, and this function right here, although they are two different functions, they agree at every single spot except for at this, in this case, this particular spot right here at x equals -3. Then they have the same limit at that point. And so it is fair for us to use this dividing out technique and evaluate the limit of some new function instead, but still say get the same answer. Okay. So when you hear dividing out technique, it's really kind of simple. It just basically means this. Let's find common factors between the basement and the attic and divide them out, and then express this new function and the limit of that, and then evaluate the limit of that function. So for instance, we say, let's go find the limit as x approaches 1 of this, okay? Of course, my first alternative would be to always kind of try to direct substitute. So we say, well, 1 minus 1 on top. It'd be 1 cubed down here minus 1 squared plus 1 minus 1. But what we end up with here is this. We get 0 on top, and we'd get 1 minus 1, plus 1 minus 1. We get 0 again. So this is this indeterminate form, okay? So if I don't have a calculator on me, perhaps then maybe we could factor the top and the bottom. So this is where paying attention in algebra comes in handy. We'll factor the basement. So we get x cubed minus x squared. I know that this is a polynomial here, so we'll try a factoring method that's called grouping. So we'll group the first two terms plus now x minus 1. And we say, okay, well, the common factor between these first two happens to be an x squared. So we get x squared, and what's left on the inside is x minus 1. And over here, the common factor between these two terms is 1. So we'll factor out of 1. And I'm left with an x minus 1. And now I notice that these two terms in the sum here have a common factor of x minus 1. So we'll factor out the x minus 1. And so we get this x minus 1, x squared plus 1. Now, this is a sum of two squares, so it is not factorable. I can't factor it. But what I know is this. We can rewrite this limit here. Let me make some room here. Is this instead? Well, this is the limit as x approaches 1 of x minus 1 was in the upstairs. And in the basement, we got this factor. We have this a factored expression, x minus 1, x squared plus 1. And we notice that these two factors here cancel out. So we can rewrite this limit again as the limit of this new function that is going to agree with all of the values of the first function except for at the one point where it's undefined. So we'd say, well, this is 1 over x squared plus 1. And the nice thing is, once we've divided out the common factor, hey, we can direct substitute here. As a matter of fact, we could just plug in 1 for every instance of x, and you would see that we get this 1 over 1 squared plus 1. In other words, we get 1 over 2. So we get a half is the limit of this function, and all we had to do is divide out common factors. And again, we could check this with a graph or a table. I'll leave that up to the viewer to kind of throw that into a graphing utility and see that it does approach a height of a half. The second limit here is just for practice. Let's go ahead and take a look at another one here. If we were to plug in 2 in every instance of x, I just want to point out here, direct substitution fails because we would get this. 2 squared plus 2 times 2 minus 8 all over 2 minus 2. So we get, well, 4 plus 4 minus 8 is 0. And then 2 minus 2 is 0. So we get indeterminate form. So what we're going to have to do is this. Let's factor the top and the bottom completely. It seems at the top we need two factors of negative 8 that add up to be a positive 2. So this must be a positive 4 and a negative 2. So we get minus 2, positive 4. And in the basement we had x minus 2. Now we're still taking the limit of this. So we still have to write that out front. The limit of this as x in this instance is approaching 2. But we notice that these common factors divide out, and so we get now the limit of some new expression, the limit as x approaches 2 of this line, this linear function, x plus 4. And so direct substituting here, we could see that we just get 2 plus 4. So our limit here is 6. Our limit here is 6. So in terms of techniques for evaluating limits of things that yield indeterminate form, one way to do it is use the dividing out technique. Cheers.